Hello students. So today we will start with the introduction of the subject, that is electromagnetic waves, which is there for your current semester. So before we begin with the subject, as I had already told in the orientation class, what is electromagnetics? So briefly, we will try to understand what is electromagnetics and why we have to study the subject of electromagnetics. So if you want me to put it briefly, electromagnetics is the study of interaction of fields generated by time varying charge distributions and currents. So this definition or this sentence, it might bring a lot of confusion in your minds as regards to the terms that have been used in this. So when we say it is a study of interaction of fields that are generated by time varying charge distributions and currents. So what is a field? So you might have some questions in your mind with regards to some different fields here. So what is a field? Okay. Just joining. So what is a field and how these fields are generated by charge distributions and currents and how do they interact? Right? So all these doubts, it comes to your mind when I say this. So this subject, when you study this subject, you will be able to answer these questions. Like what is a field? How are fields generated? What are charges? And how the charges and currents, they generate the fields and how the fields interact with each other, okay, and with the surroundings. So these questions will be answered when you study this particular subject, that is electromagnetics. And why we have to study this subject? Why study electromagnetics? So this subject, it acts as the foundation for your further communication subjects that you are going to study in the upcoming semesters, including microwaves and antennas, radar communication, or fiber optics. Today, communication, it's so advanced, and today we have different levels of communication and different applications of communication. And for all this to come through, the role of electromagnetic waves is very, very important. So as you know, much of the things, it's much of the world's traffic is actually carried by fiber optics. Almost 99% of the world's traffic is carried by fiber optics. And what is the core? What is there in the core of these optical fibers? It is actually the electromagnetic waves, right? So these electromagnetic waves, if you want to know the applications of electromagnetics, there is a short video which I can play it for you. Okay. I hope this screen is visible.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel every day, everywhere you go. It is odorless and tasteless, yet we use it and depend on it every hour of every day. Without it, the world you know would not exist. What is it? Electromagnetic radiation. These waves spread across the spectrum from very short gamma ultraviolet, visible light waves, even longer infrared, microwave, to radio waves, which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, EM waves, are simple motion waves and are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel to the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billions of nanometers. The number of these crests that pass a point within 1 second is described as the length of wave. One wave, or cycle, per second, is called a hertz. Long EM shorter. Gamma waves are the shortest, highest energy waves in the sector. So, as you see also not only are there like waves from the TV striking prize, but also radio waves transmitted from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the car is driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Simulate your tuning a radio to a specific radio station. Our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light of the spectrum. Objects appear to have colors because the wavelengths interact with the molecule. Some wavelengths within the spectrum are reflected, and other wavelengths are absorbed. This means the screen because EM waves interact with chlorophyll molecules. And 577 nanometers are reflected. Our eye interprets this as green to be green. Our eyes see the leaf as green, but can not tell us anything about how it reflects ultraviolet, microwave, or infrared wave. To learn more about the world around us, scientists and engineers have devised for us to see as the spectrum all through our life. We have multiple wavelengths outside the spectrum from inside our eye, from seasonal shades to specific habitats. Every habitat reflects and absorbs the radiation differently based on composition, a graph of the range of
Okay. So that was a very small video. It was actually by that video is by NASA. There, they have told the applications of electromagnetic waves as per what they do. Okay, so based on the activities carried out by NASA. So further part of the video is related to that. So I just showed you only some parts, which covered the topics of electromagnetics. So as you can see, we can see these electromagnetic waves everywhere. So it is very important for us to study that in order to use it for our convenience. Okay, so we will see how this syllabus is organized, or the scheme of the subject, the subject core and other things as given by VTU, 18 EC 55, and just like other subjects, it's for 60 marks external, 40 marks internal, and the credits for this subject is 3. So it's a 3-credit course. So these are the learning objectives as given by the university. So this subject, it will enable you to study the different coordinate systems, okay, and the physical significance of these terms, or you can say these operations like divergence, curl, and gradient. We will be looking at all of this. Then to understand the applications of Coulomb's law and Gauss's law. These laws, you have already studied in physics in your high school or maybe in your PUC, Coulomb's law and Gauss's law. So we are going to apply this to different charge distributions like point charge, volume charge, surface charge, line charge. Okay. So and the applications of Laplace's and Poisson's equations, we are going to derive these Laplace's and Poisson's equation and apply them to solve real-time problems on capacitance of different charge distributions. Then to understand the physical significance of Biot-Savart's law, Ampere's law, and Stokes' theorem for different current distributions. Then to infer the effects of magnetic forces, materials, and inductance. So we are going to study the concepts of electric fields as well as magnetic fields. When it comes to electric fields, we deal with the capacitance. When we come to the magnetic fields, we deal with the inductance. Okay. So then to know the physical interpretation of Maxwell's equations, we are going to study or derive these equations, Maxwell's equations, and apply them for waves, uniform plane waves, for their behavior in different media, maybe free space or maybe conductors or dielectrics, that is insulators and other media. Okay. Then to acquire knowledge of Poynting theorem and its application of power flow. So all these things we are going to deal with. So these are the objectives of this course. So just like any other subject, we have 5 modules here. Okay. So briefly we will see what we cover in these modules. In the first module, we have the revision of vector calculus, because most of the quantities that we are going to study in this subject are vectors. It may be a field, okay, so it may be current density, it may be yeah, flux density, so different things, force, whatever. So all these things, the power, all these things, they come in the form of vector. So understanding the concept of vector and the operations on vector, there are different operations like what happens when you add the vectors, okay, multiplication of vectors, finding vector product, dot product, cross product. Okay, so then we also have the different coordinate systems. We are going to study that in vector calculus. We have different coordinate systems like rectangular coordinates. We also call it as Cartesian coordinate system. Then we have cylindrical coordinates and spherical coordinates. So as I said in the orientation class, so you need to have a very good imagination in order to understand this subject. So what happens is, we draw things on a board. We are limited by some resources. We draw the things on a board, or I might draw it on a screen. So whatever, you might see it on a screen, but you should be able to imagine it in 3D, just like it appears in front of you in 3 dimensions. So these coordinate systems are very, very important. Whatever you study in the first module, as in the revision of vector calculus, these coordinate systems, based on this, the entire subject, it's based on this, okay, based on the coordinate system and how you understand the coordinate systems. So then you have Coulomb's law, electric field intensity and flux density. So Coulomb's law, you already studied, it actually gives the expression for the force that is exerted by a point charge on any other point charge that is placed in its field, right? So then we will see electric field intensity and the field due to different types of charge distributions like line charge, sheet charge, and volume charge. Then we will see the concept of electric flux and electric flux density, and we will go through the numerical problems, numerical examples. So what we have in this subject is more than 50% of the question paper will be numerical examples. So you need to understand the concepts in order to solve the numerical examples. Then in the second module, we extend this concept of electric flux, for the Gauss's law. Gauss's law, it actually gives the electric flux enclosed within a closed surface. Okay, then application of this Gauss's law to point charge, line charge, surface charge, volume charge, different types of charge distributions. We have a point charge, line charge, surface charge, and volume charge. Okay. Then different forms of Gauss's law, that is point form of Gauss's law. Then divergence, we understand or we go through the concept of divergence. Then we have Maxwell's first equation in electrostatics. Then the vector operator del, this is the operator del. Okay, it's actually when you perform this operation, we get the divergence of a particular vector or a particular quantity, and the divergence theorem, then again numerical problems. Then in the same module, we also have the concept of energy or the work done in moving a point charge in an electric field. Okay. Then the line integral, then potential and potential difference, then the potential field of a point charge and potential gradient. So we also extend this for current density and continuity of current. So all these things we cover in second module. So then we have very important equations, Poisson's and Laplace's equation. So we derive this Poisson's and Laplace equation, and we have one theorem of uniqueness theorem, and we also see the examples of solutions of Laplace equation along with some numerical problems. So till up to this, whatever we have, Poisson's and Laplace equation, up to this part of module 3 from the beginning, that comes under, you can say, a broad topic called electrostatics. So where we deal with a static electric field, okay, a static electric field. Next concepts, that is a steady magnetic field. Here we start dealing with another kind of field, that is magnetic field. Till now, till this particular point of Laplace and Poisson's equations, we will be seeing only electric fields. So then we will start with the magnetic fields. So again, here there are different laws which are on the similar lines as you'll be seeing in electric fields. Okay, that is Biot-Savart law, Ampere's circuit law, Stokes theorem. Then you have a concept of curl. Okay, then just like electric flux, we had that. Here we will have magnetic flux and magnetic flux density. Then potential, magnetic potential, scalar and vector magnetic potentials. Okay, so in the next module we will deal with the force on a moving charge, magnetic force on a moving charge, differential current elements, the force between differential current elements. Okay, then magnetic materials, the properties of them, that is magnetization and permeability, the boundary conditions, then the magnetic circuit, then again energy, potential energy and forces on magnetic materials, then the concept of inductance and mutual reactance. So we will also study Faraday's law of electromagnetic induction in integral form as well as in the point form. Okay, so if you extend these Faraday's law, you'll get Maxwell's equations. That comes in the next topic, that is Maxwell's equations. In Maxwell's equations, we're going to deal with the continuity equation, then inconsistency of Ampere's law with continuity equation. We have already studied the Ampere's law. Okay, so that law, we will show that it is not consistent. Okay, or there is some missing link in the Ampere's law, and we will try to fix that link. Then there is displacement current, conduction current, different types of currents. Then equations, we are going to derive this Maxwell's equation in point form and integral form, and also we will see the equations for different media along with some numerical examples. Then we have the last part, we will have the waves, uniform plane wave, derivation of wave equations. Starting from Maxwell's equation, we are supposed to derive the wave equation. Then the solution of these wave equations for perfect dielectric, the relation between E and H. E stands for electric field, H stands for the magnetic field. And the propagation of wave in different medium, like in free space, good conductors, and insulators. The solution of wave equation for sinusoidal excitation, propagation in conducting media, okay, with different parameters. So we're going to see them, propagation constant and other things, and good conductors. The skin effect or the depth of penetration. Then we are going to study another important and the last theorem we are going to see in this subject is Poynting's theorem and the equation for the power of the wave. Okay, so what we'll be seeing is much of it will be derivations of certain expressions. Okay, whatever the concepts we are going to see, then we are going to solve some numerical examples based on the understanding of the concepts. Okay, so these are the outcomes of expected outcomes of what we are supposed to get after studying this subject. So a student, he should be able to evaluate problems on electrostatic force, electric field due to different types of charge distributions like point charge, linear charge or line charge, surface charge, volume charges by applying conventional methods and charge in the volume. Okay. Then you should be able to apply Gauss's law to evaluate electric fields due to different charge distributions by using divergence theorem. Then to determine potential and energy with respect to a point charge and capacitance using Laplace equation and apply Biot-Savart's and Ampere's laws for evaluating magnetic field for different current configurations. And also you should be able to calculate magnetic force and potential energy with respect to magnetic materials and voltage induced in electric circuits. And apply Maxwell's equations for time-varying fields, electromagnetic waves and free space and conductors, and also to evaluate power associated with EM waves using the Poynting's theorem. So these are the outcomes that we will be able to achieve after the completion of this subject. Okay, so overall, and this is the textbook that is prescribed by the university, that is Engineering Electromagnetics. The authors are W.H. Haight and J.A. Buck. Different editions are available. 8th edition is described in the syllabus, but previous editions are also available. 7th edition, 6th edition, they are all very similar. The content is the same. Okay, you can. This is a very good book by Haight and Buck. You can refer this textbook for this subject. So, if you want to brief everything that is there in the syllabus, briefly we can put it under these 4 categories. That is electrostatics, magnetostatics, the time-varying fields, and the waves. As I said, the initial topics that we are going to see up to the Poisson's and Laplace's equation, the Coulomb's law, electric field intensity, electric flux density. Okay, so here we have the electric field and electric flux, then the capacitance. So all these things till Poisson's equation, that comes under electrostatics. Here we are studying only a static electric field, that is electric field because of a static charge which is not in a motion, which is not moving. Static electric field means electric field because of a static charge. A static charge is a charge which is at a particular place, which is not moving. Okay, so that is electrostatics. Next concept, next category, what we have is magnetostatics. In magnetostatics, we are going to deal with the steady magnetic field and the concepts related with that. Steady magnetic fields means the magnetic field, it is generated by a moving charge. Okay, so it is steadily moving. Okay, which is not dependent on time. Okay, which is moving steadily with respect to time. That is a steady magnetic field. So that is called a magnetostatics. The study of that is called magnetostatics. Then we have the concept of time varying fields. Till this particular point of electrostatics and magnetostatics, while studying electrostatics, we have been studying only electric field. While studying magnetostatics, we'll be dealing only with the magnetic fields and effect of electric field on magnetic field, but we are not considering the time factor. But if the fields vary with respect to time, all the things are going to change. So all the equations that we deal with or that we study in electrostatics and magnetostatics, we will come to know that there is something wrong in them. That is, there is some lacuna or some factor or some missing link. And that missing link we are going to fix in this particular concept of time varying fields. And that is only in the 5th module when you study Maxwell's equation, we are going to find the inconsistency of whatever we have studied, and we are going to fix those equations by adding some factor. Okay, so when the fields vary with respect to time, we have to correct the equations whatever we have studied, and those equations what we get, those are called the Maxwell's equations. And yeah, we are going to study the Faraday's law. That actually comes in the magnetic materials. When you extend the Faraday's law, you get these Maxwell's equations. And then using these Maxwell's equations, we are going to derive the equations for the waves. Okay, we are going to derive the equations for the waves. Yeah, what is wave? Wave is nothing but something, some energy in motion. The electric fields and magnetic fields, when they are moving, they form the waves. Okay, so what you can see, this what we have seen in the video, they are the electromagnetic waves which have electric as well as magnetic fields, and these fields they are mutually perpendicular to each other. Okay, we are going to study this one by one. So this is the overview of the subject. Okay, so we will begin the first module. I will begin the first module in the next class. Fine, so probably tomorrow.